Hi, this is Dr. S.P. Arsa from Mechanical and Industrial Department, IIT Roorkee. I am going to deliver my lecture 10 of the subject of the strength of material, which is developed under the National Program on Technological Enhanced Learning. I just want to refresh those you see in the previous lecture which we discussed about that what exactly the the strains are. If you want to measure the strain, then you see what the analytical as well as the graphical solution was there. So, in the previous lecture, if you just focus, then you see we found that the Mohr strain circle as well as the Mohr stress circle are pretty similar. Like on the x axis, again the similar this normal strain component is there, and the shear strain component is there on the y axis, and how to get the how to extract the information from the Mohr circle. This is pretty similar to like the Mohr stress circle, where you see the sigma means the normal stress component was there, or the shear stress component are there on the y axis. Then we also found that that though we can measure the strains, you see, because we cannot measure the stress, we can measure the strain, but again you see, to measure the strain, the angle is very important. So, you see we need to put only the single strain gauge, because we always strain gauge is the technical the instrument is there to measure the strain. Single strain gauge is not at all comfortable to measure all the three kinds of strains. So, you see here we need to put the minimum three strain gauges to measure the respective normal as well as the shear strain components. And then you see the strain rosette comes in the picture, where the three strain gauges are to be well set up at 45 degree or at 60 degree. So, at 45 degree you see we establish the relations with the using of the three different the algebraic equations are there at the oblique plane strains, normal as well as the parallel. So, we found that at axial part, if we are talking about the 45 degree strain rosette, then at x axis or at y axis we have the strain component pretty symmetric, like it's straight. You see the direct strain components are there, but you see at the middle portion where exactly you see the 45 degree the axis is there, and at this particular axis if we have the strain rosette, then you see this will give you the strain the shear strain component, this gamma xy, which is you see exactly equals to what the direct impacts are there of the other two components. Meaning is very simple, like if you want to measure the strain the shear strain, then it was nothing but you see that if we have the middle portion, the 2 times of the normal strain at the middle portion minus sum of the axial, this x and y strain, epsilon x plus epsilon y. Meaning is pretty simple, that if we want to measure the three different component of the strains, we always need the minimum 3 strain gauges, and they need to put at the strain rosette formation either respective of the 45 degree or the 60 degree. And then you see we found that you see there are some of the principal strains are there, and the principal strains are always exactly analog is there as compared to the principal stresses, and then also we can find it out that actually where the maximum shear strains are there. So, this kind of the relations, and we also solve one numerical problems to draw the Mohr strain circle, that actually what exactly the information which we needed to draw the Mohr strain circle, and you see what we can extract the remaining information from the strain just by measuring. You do not have to calculate numerically, but only you need to measure the things like what are the coordinates, what are you see the radius, as well as you see the angle and all those blah blah things. You can easily find it out by simply measuring those distances as well as the angles. So, this was you see the kind of discussion which we did in the previous lecture. So, in this lecture now we if you go up to the previous parts, then you see we have now lots of information about the basics of the strength of material, like we know the stresses, we know the strains, we know in between the relation between the stresses and strain, if you see the material application is there under the elastic. But still you see we know the properties of these stresses and strain, but still you see if these load applications are there on the different material, then how these the relations are there in between the stresses and strains, we do not know. So, in this lecture you see we just trying to first visualize that what kind of materials are exhibiting the different kind of properties, or we can say this kind of the stresses or strains, or this Young's modulus of elasticity, or this Poisson ratios, or this kind of you see all this either elastic or plastic deformations are there. So, what type of materials are available and how we can categorize those materials in terms of the properties, in terms of their exhibitions under the load and all that kind of things. So, in this lecture you see we are going to discuss those things. So, you see here first stress strain relationship based on the different materials. So, first stress strain relations, the Hooke's law basic, you see if you are talking about the elastic deformation, then Hooke's law always gives you the stress strain relationship between the elastic limit, and it says that stress is proportional to strain under the elastic limit. Since for the most of the material is exhibiting this kind of thing, it is impossible to describe the entire stress strain curve with the simple mathematical expression, because you see when you apply the load irrespective of the tensile or compressive, we don't know what will happen beyond that. So you see we cannot put all the time the mathematical expressions and get the final, okay, now this is up to the rupture point. So what we always need that actually what exactly the material properties are there and how they are exhibiting on this stress strain relationship. So in any given problem, the behavior of material is represented by idealized stress strain curve. So we always need the graphical part, that how they are exhibiting, and that's why you see the universal tensile testing machine, you can say UTM, is always giving you whether the tensile test is there, the compression test is there, the bending test is there, whatever the kind of tests are there, you can simply get the you can simply plot those curves with the using of, you see these like the props, or we can say with the using of this UTM, and these curves are known as the idealized stress strain curve, which emphasize those aspects of the behavior which are the most important in a particular problem. Because you see, if let us say if you want to design something, and in the design the basic feature is that actually what the important part of what the important material properties are, and based on those properties you can simply find it out that okay, now this material can sustain this much stresses, if you apply the load, it can go up to this extension without any permanent failure or permanent rupture. So you can go that okay, now this is good for this kind of application, this is good for this kind of application, and based on that you see we need to be very careful that what exactly the material properties are there and which material is really to be chosen to get the desired output. So here you see we are categorizing those material based on the these stress strain curve properties. So first material which we are talking about, that is the linear elastic material. A linear elastic material is one in which the strain is proportional to the stress. Means you see, if you see this particular the curve, you will find that we have the strain epsilon, we have the sigma stress, and you see if you apply the load, it will simply extended. So means you see the stresses are also coming, inducing by the application of load, at the same time we have the extension, means we have the deformation in that particular object. So we can simply, if you want to put the relationship between these kind of in between the stress and strains for this kind of material, you can simply put by the straight line. So you see we have the straight line for this kind of material where the sigma and epsilon is there. So this kind of material is always known as the linear elastic material, and generally you see the rubbers are there, or we can say some different kind of this polymers are also there, which easily show the kind of elastic, we can say these are the perfect elastic material in which apply the load, it will extend it straight way. So you see it will simply distort it, or we can say the kind of deformation is straight way come once you apply the load. So you see kind of this kind of materials are there, which is known as the linear elastic material, in which the stress is proportional to strain up to the limit. Second is there, that is the rigid material. Rigid means like the stone is there, apply the load, apply the load, apply the load, it will sustain up to a means there is no deformation, like you see even if you apply the load and then suddenly it ruptured. So it is one of the the kind of material which do not experience any strain regardless of the applied stress. So you see we are applying the load, but there is no kind of deformation is there within the microstructure or externally applied kind of that. That means you see whatever the surrounding is there, there is no change of the shape of the material irrespective of what the load application is there or the stress applications are there. So you see here this curve will simply blank because nothing will happen even if we apply the load in terms of the stresses, in terms of the strain, nothing will come. So it is a blank kind of that. So rigid materials are always exhibiting they are exhibiting zero result irrespective of the stress and strain. So we cannot set up any relationship between the stress and strain in this kind of material. The third is the perfectly plastic. Perfectly plastic means there is no strain hardening, like you see perfectly plastic straight way you go to straight way when you apply the load, it will permanently sort of deformation is there, means there is no kind of once you release the load, body comes to its original state, nothing will happen. Once you apply the load, permanently deformed, like you see if you are taking a thin wire, once you apply the load it will simply bend, and you see even if you apply the load it will bend, and that you see like the perfectly means whatever the load application is there, once a permanent set of deformation exists, this will continue up to the extreme point. So you see a perfectly plastic body that is the non-strain hardening material is like this kind of material is there, where the strain, it will just approaches to the maximum, like this shear stress, this normal stress component is there. So the stress is at maximum and the deformation straight way you see here, this deformation is constant, means once it is deformed it will continually like go, even you see the this kind of deformation, or we can say the strain will increase, keep on these things without any addition of the stress particle. So it is, that's why it is known as the non-strain hardening, means there is no hardening is there due to the strain, it is simply like showing the straight line towards the strain side like that. Then you see we have a rigid plastic material. So rigid plastic says that you see, though it is a plastic material, but some sort of the strain hardening is there. That means you see a rigid plastic material or the strain hardening is like can show some sort of a variation in the strain part irrespective of the stresses also. So you see here straight away when you apply the load, though it is a plastic material, so it has a permanent set of deformation right away when the load application is there, but again you see when we increase the load there is an increase in the stresses, the simultaneous effect means the simultaneous increase in the strain also. So you see we can say this kind of strain hardening is there. Then we have, which is a pretty common thing sometimes, elastic perfectly plastic material, means you see the material is also having elastic properties, but as we keep on like increasing the load, it shows the perfectly plastic material. So you see here the elastic perfectly plastic material is having this kind of characteristic. So we have the stress strain curve, on the stress and strain up to the elastic limit, you see it will exhibit the proportional limit with the stress and strain. So up to this point we can say that the elastic limit, and then it is a perfectly plastic, means you see perfectly plastic means there is no strain hardening after this point. So we have the constant line in that particular phase. So there is no, you see like the stresses are coming in that, only the deformation will go on keeping. So this is known as the perfectly plastic with the elastic nature of the material. Then we have the last one, that is a pretty common, you see the ductile materials are there generally, and they are showing this kind of like mild steel is there, high carbon steel is there, high speed is there. That is generally we are saying that these are the elastic plastic material, means you see it is showing like to a certain point the elastic nature, it is showing up to a certain nature of plastic nature, in which you see we can say the strain hardening is also available. We have the elastic region, we have the plastic region, and we can easily locate these regions at the two different set of points. So the elastic plastic material exhibits the stress versus strain diagram, which is a very common like the diagram, like this is the stress and this is strain. So we can say this up to a certain limit there is a straight portion is there, this is the perfectly elastic portion, and once you see it goes beyond certain point, then we have you see a kind of nonlinear relation is there. So this is the straight relation, we can see the linear relation is then between the stress and strain, and beyond this point we have a nonlinear relation between the stress and strain, and that is known as the plastic region. So you see we have two different regions if we have a material of a nature of elastic and plastic, and we simply like by putting the experimentation we can easily like separate it out the different regions of the elastic as well as the plastic. And generally, as I told you that actually irrespective of whether it's a mild steel, high carbon steel, high speed steel, they are generally showing this kind of relationship between the stress and strain, and we can simply get with the using of universal testing machine if the tensile is there, compressive is there, or bending is there. So this is a very common diagram for showing the relationship between the stress and strain for a kind of elastic plastic material. So you see here whatever we discussed, you see right from the perfectly elastic to perfectly plastic to you see like the elastic plastic where in the elastic some perfectly plastics there, or you see we have a general elastic plastic material. All those curves are simply showing a different kind of relationship between the elastic and plastic in between the stress and strain based on what exactly the elasticity is there, plasticity is there, or the combination of there. So you see how microstructure is playing a key role when the application of load is there in terms of the stresses or in terms of the deformation means the strains. This is a very important phenomena as far. So now come to the elastic like stresses and strain, means if you are talking about only the elastic region, then what exactly the relation is there in between the stresses and the strain. So previously Stress strain relations were considered for the special case of uniaxial loading. Means you see, if we have a kind of uniaxial, means the direct stresses are there. Uniaxial loading is there in terms of, you see, we can say the pulling or compression, that is axial or the normal component of the stress was coming into the picture. That means you see, we are simply like considering the elastic limit first, and also we are considering that the load application is towards the axial. There is no eccentricity or there is no parallel forces are there in that particular component during the load application. In this section also we shall generalize the elastic behavior, what the the particular elasticity is there when the application of load is there within the elastic limit, so as to achieve the relation between relation which convert all the 6 component of the stresses, because it is a plane stress. So we have, you see, the 6 component, 3 normal stress, 3 shear stress components are there with the 6 component of the elastic stresses. So you see, we have all the kind of stresses, means all the components are there, because we are not though we are considering the tensor part of the stress, but here we are also assuming at the same point that it is a plane stress and only 6 components are there because of the symmetricity. So you see, we just want to convert those things in generalized way, the state of the stress, that what the 6 components are there of the stress and how they are behaving when we are talking about the elastic behavior part. So first of all, you see, in this category the first key feature is there if we are talking about a isotropic property of a material. Means you see, we have a ductile material, but if it is showing the isotropic one, if the response of a material is independent of the orientation of the load axis, okay, of the sample, then we can say that the material is isotropic. Isotropic means, you see, irrespective of what the orientation is there, at what angle it is putting, or what kind of load application is there, it is whether in the x direction, y direction, z direction, you see the load application is there, irrespective of what the load application or in which direction it is there, if whatever the responses are coming, if they are, you see, perfectly same in all directions, we can say that this kind of material is known as the isotropic material. Or in other words, we can say the isotropy of a material in a characteristics which gives us the information about the properties are same in all 3 orthogonal or the mutually perpendicular direction x, y, z, or we can say if the response is dependent on the orientation, this is known as the, means it is just the reverse side, that an isotropy. Means you see, isotropy material is that kind of material, rather you see, if you put any kind of load in any direction at any angle, even I should say, then the material properties are same, it is independent of the orientation of the load application on the element. This material is known as the isotropy. And if a material is very much sensitive to the load application, at what point of application is there, at what angle they are simply applying the load, this material property is known as the anisotropy. So this is, you see, the both kind of features are. Example of an isotropy material, because you see this is a very good property that you see, sometimes it is showing, then these are, you see, the anisotropy material which are, which are not showing this kind of relation, which are very, very dependent on that what the load applications are there, and they are exhibiting all different properties in the different directions. These examples of anisotropy materials are wood. Wood, you can see, if we apply the load sometimes, and that is why you see the woods are characterizing. Sometimes woods are always strengthened, various types of woods are there. Some types of woods are very much strengthened towards the axial loading, sometimes they are very much strengthened towards the compressive loading, and that is why according to the applications are there, that which layers are supporting what type of forces. So accordingly, you see, we are also characterizing that actually since they are exhibiting the different material properties in the different directions, so always you see we are categorizing this wood in an isotropic material. And then you see fiber reinforced plastic. These the fiber operated, these reinforced plastics are always forming in that way that they are supporting some compressive loading, or sometimes it is tensile loading, so that the layer formations are in such a way that these fiber layers are supporting in a different directional forces. So that you see, since they are forming in that way only, that they are supporting different properties in different directions. So always you see, we can categorize this fiber reinforced plastic in the an isotropic material. And then you see, it's a pretty common example is the reinforced concrete, and that's why you see the concrete material we are keeping in the railway tracks, that you see they can simply compress, you see, or they can absorb the axial vibrations. So you see they have a very good compressive, or we can say the axial part is there. So always this is the perfect example of anisotropy material, that they are very much, they are always good in the axial, or we can say the compressive part. So they are, you see, actually they are showing some good properties in that direction, and they are not showing the similar kind of trend or similar kind of property in the other directions. So these are, you see, the some of the 3 examples which are exhibiting the different material property in the different directions. So you see, so this was the first property which is a very common property and which is a very popular property was there, that isotropic property. Then you see we have the next property is the homogeneous property. A material is homogeneous. Homogeneous means, it's a kind of homogeneous mixture kind of thing is there. So if it has the same composition throughout our body, like you see our cell is there. If you take any part of our body and if you just take it out of the cell, you will find that the cell characteristics are homogeneous for a unit body. So similarly, you see, we can say that the material is homogeneous because if it has a same composition throughout this particular material body. Hence the elastic property are same at every point in the body. Means, you see, because as you apply the load, since they have the same composition, so definitely they will exhibit the similar kind of properties under the same application of load is. However, the properties need not to be the same in directions of the material, just like you see in the isotropic. So this is the clear difference. Though you see, it will show the properties same at every point, but that doesn't mean that actually these properties are similar in all 3 directions. Might be sometimes, the properties are different in different directions. So homogeneous material are those material which has the same composition, and because of the same composition, the elastic properties are same at every point of body, but that doesn't mean that they are same in all 3 directions. Okay. So isotropic materials have the same elastic property in all directions. So that's the beauty of these elastic properties are, so they are exhibiting all the properties the similar kind of properties in the different directions also. But here you see the homogeneous materials are showing the different properties in the different directions, though they have at individual points. At any point in the body, they are exhibiting the similar kind of the elastic properties because of the homogeneous mixture or homogeneous composition of the material within those bodies. Therefore, the material must be both homogeneous as well as the isotropic in order to have the lateral strain to be same at every point in a perpendicular or at a particular component. That means, you see, if you have the lateral strains and the longitudinal, means if you have a longitudinal strain and lateral strain, if you are saying that actually these are same at every point, then it must be first homogeneous, just to have the same elastic properties at all points, and also it should be having the similar isotropic material, so that they will have the similar kind of these elastic properties in the all directions. So the elastic properties must be same in all directions and must be same at all points. Then we can say that the lateral strains are similar at every point of this kind of material, and that's why you see generally we are preferred to have a material homogeneous as well as the isotropic properties. Then you see after incorporating both the properties, like you see the homogeneous as well as the isotropic, we can say that the strains are proportional to stress. Strains we can easily measure with the using of strain gauges or rosette. Young's modulus, as we discussed, that it's a property of material, so it has a different value altogether for the different material. Like you see, as we discussed in the previous case, that there are 6 types of materials are there, like it's a perfectly rigid or perfectly elastic or perfectly plastic or elastic perfectly plastic or elastic plastic. So you see based on that, the Young's modulus of elasticity is having different the values. So once you have the strain which is measured part, once you have the Young's modulus of elasticity which is especially properties of material, you can easily get the stress part, which is you see the sigma is epsilon into E. Or we can say, we can also get the Young's modulus, this Poisson ratio, which is nothing but equals to minus of this epsilon lateral divided by epsilon axial. Means you see whatever the kind of deformation is there, absolutely based on that what the isotropy and homogeneous things are there, because if it is not exactly equal in all the direction, then definitely you see it will exhibit the Poisson ratio, which is has the which has a different meaning for minus epsilon lateral, means what the deformation is there in the x direction and what the deformation is there in the other mutually perpendicular direction irrespective of y or z. So this is this kind of discussion which even discuss that this homogeneous or isotropic part is there, which is exactly similar to this kind of mathematical expressions. So now you see, since we are talking about the elastic material, So we need to like go for a generalized Hooke's law. So these are like some of the equations which express the relationship between the stress strains within this elastic region. That's why we are saying that the Hooke's law for uniaxial state of stress only when the stress is not greater than the proportional limit, because you see once it goes beyond to the proportional limit, means when the stress is not proportional to strain, then you see that means we have a kind of the permanent set of deformations are starting to exhibit. That means you see like we have the microstructure which has a kind of dip or which has a kind of like the deviation is there in between those microstructures. So we can say that then these uniaxial state of stress like is not exactly proportional things. That means the Hooke's law is not valid for those kind of the stress and stress relationships. So in order to analyze the deformed like the this deformational effects producing by all the stresses, we shall consider the effects of one axial stress at a time. Since you see we like presumably are dealing with the strains of the order of 1% or even less, then that means you see we have to be very careful that actually whether we are going beyond certain reason like beyond certain point or not actually, because if we are like dealing with the small limits of these strains and stresses, that means like whatever the deformable properties are there, or I should say actually whatever these elastic limits are there, this is well stabilized and we can say the Hooke's law is valid for this kind of relationship. And we can say that these effect can be also superimposed arbitrarily, because you see when we this to locate the reasons that okay now this is the proportional limit, and then you see the transition region starts that okay sometimes it is showing the elastic, sometimes plastic, and then you see the plastic region starts. So if you see it is very much like it is not an easy task to exactly like find out those locations. So you see these effects, whatever the effects are there of the elastic, plastic or in between that are really like superimposing those things. It is always taking arbitrarily like that. So now you see we can simply show the like the triaxial state of stress in generalized way in this particular figure. Like as we discussed in this, we have the three mutually perpendicular stresses x, y and z, and you see like in those things always two mutually perpendicular stresses are there. These are the axial stresses sigma x and sigma y, and you see we have the tau x y. So if you want to express those things in like the tensor way in which there are the 9 components, so we can also show all those things in a generalized unit cube way. So here it is, you see we have it is just kind of you see the refresh those things that this is my plane where you see the normal stress components are there. So this is you see the sigma x because it's a normal to this particular plane, and then you see the parallel stresses are there, either we can say the gamma xz or gamma xy, it is in the x domain. Similarly we can like drag this information for other two domains, like if you are talking about the y domain, then you see we have the sigma y which is perpendicular to this plane, and then we also have this tau yz and tau yx. That means you see these two parallel forces are there which are like influencing the shear stresses in this nature, and we this in normal stress component is there which always inducing the normal stress component towards this body. And similar you see you can this drag the information for the z axis where this is the plane normal to the plane, you see this sigma z is there, and then when the forces are set parallelly, then tau zx, tau zy and tau zx will give you the clear cut idea about that how these stress formations are then, how these stresses are being well set up. Because now you see here it is not exactly equal in all three directions, meaning is that the if the force is the force point of this application of the force is different in different like directions, then we have all three directional stresses, and these like the nature of the stress is different as you can see here, and the magnitude is also depends on that what the effective area is there and the force application is. So now you see like if you apply those concept into the main category, then you see we have like let us consider a case where sigma x is simply acting. That means you see we have a simple axial pulling is there, only the force is dominating in the x direction, and then what will happen means what exactly the deformations are there, that we will see in this particular diagram. So here it is, you see we have a simple crossbar. In the crossbar you see if we are dragging towards outside, then we have this tensile loading is there towards towards outward direction, and due to that there is a contraction in that in the lateral part. So the longitudinal stress is sigma x, but while you see in the lateral part there is a kind of contractions are there, so it will cause an increase in dimension in x like direction, whereas the dimension y and z will be decreased. So the given figure clearly shows that there is an axial loading is there in the x direction, while there is a contraction is there in the other direction, because if the axial loading is there in the x direction, there is a pulling side, there is an extension is there in the x direction. So we can compute the strain component in all three directions, that because of the axial loading only. So we have, you see now the things, the resulting strains in all three directions are, because we are pulling in the x direction, so straight away the strain will come, the normal strain will come, or we can say the direct strain will come in the x direction, that is epsilon x is nothing but equals to sigma x by E, because we can straight away measure that part, the extension. But you see there is a contraction is there in the other two direction, and you see if you want to set the relationship between the lateral strain as well as the longitudinal strain, then always we need to consider the Poisson ratio. So with the consideration of the Poisson ratio, we can take the strain component in the y direction. So epsilon y is nothing but equals to minus mu times of epsilon x. So now you see, you know the epsilon x. So what will happen? What the contraction is there due to the Poisson ratio? This Poisson ratio is computing the total the ratio of lateral strain to the longitudinal strain to this lateral strain. That means you see how much contraction is there, we can easily compute with this particular coefficient, this Poisson ratio into epsilon x, or we can say epsilon z also in z direction. We can also calculate the strain component here, that is equals to minus mu times of epsilon x. Meaning is pretty simple, that once you have the epsilon x, where because this is my axial loading and it's a pulling kind of that is there, we can straightway get the sigma x by E epsilon x. Once you have the epsilon x, by using the Poisson ratio, you can get the epsilon y as well as the epsilon z also. Similarly, you can like by keeping those things, you can even have those things that epsilon x is nothing but equals to sigma x by y, sigma x by E, or we can say epsilon y is nothing but equals to minus mu times of epsilon x, or we can say sigma x by E, or epsilon z is nothing but equals to minus mu times of epsilon x, or we can say minus mu times of sigma x by E, by simply manipulating the this particular relations. That means you see we can easily get the three components of strains, the direct strains epsilon x, epsilon y, epsilon z, even if it is loading in z the x direction. So similarly, you see if you are talking about the y direction, like that, if the normal stress component is there in the vertical direction, means you see now I am pulling from the vertical direction, and there is, you see, the extension is there in the y direction. So then what will be the impact? So you can see the figure here, that we have the rectangular bar is there, and from the extreme corner there is an extension. So sigma y is there, and due to that you can see this the kind of extension here. So this is the extension 1, this is the extension 2. So once you have the extension in y direction, straight away you can calculate the strain component in the y direction, and that strain component is known as the linear strain or the normal strain. So it is equals to sigma y by E, or you can say, you see, the remaining part which is contracting. So using the Poisson ratio, as we discussed in the previous case, again using the Poisson ratio we can calculate the strain component in the other two directions. So epsilon x is nothing but equals to minus mu times of epsilon y, epsilon z is equals to minus mu times of epsilon z, or we can say epsilon y, which is the main the coordinating, I should say, the dimension, because the load application is there from that plane only. So which is equals to sigma y by E. So you see here epsilon x is also can be calculated with the using of the required this available information, minus mu times of sigma y by E, and epsilon z it can be also calculated by mu times of sigma y by E. So these, you see, again, just the load application is there in the one direction, but we have the the strain component in the three mutually perpendicular direction, that what the required deformation is going on, or what the required, you see, the change of dimension is there due to the effect of one axial loading. And similarly, we can go for the other third direction, that is the z direction. So now if we consider the stress sigma z along the z direction, then again you see the required the strains again will come in all three directions, and that will be equals to, you see, epsilon z, which is equals to sigma z by E, because this is the dominating parameter through which the this deformation, or we can say the deviation, is gonna on. And then you see the other parameters will come as sigma E by z minus mu times of sigma z minus mu times of this is sigma z for other two direction, irrespective of the epsilon y or epsilon x. So if I compute that part, then you have epsilon z, which is equals to sigma z by E, but epsilon x is minus mu times of sigma z by E, and epsilon y is nothing but minus mu times of sigma z by E. Meaning is pretty simple. the load application is the individual load application is there in all x, the y and z direction, but there is an impact of, even if you are taking the individual component, it is an impact of other two directions also, and which we can compute. So if I am saying that actually all three mutually like perpendicular directions are actively like attaining, and the load application is there in the respective directions, so we can say that the total strain in any of the one direction at any point, if the load application is there in all three directions, then you see epsilon x is nothing but equals to sigma x by E minus mu by E, because you see like now the again you see the very important feature is that this load application is under the elastic limit only. So minus mu by E, the Young's modulus of elasticity, times sigma y plus sigma z. So you see other two like the stress components are always present in the extension of x direction, but they will come with the modulus of elasticity as well as the Poisson ratio. Similarly, you see in that manner also we can contain like the total strain component in y and z direction as well. So epsilon y is nothing but equals to the main coordinating parameter sigma y by E minus the combination of other two direction minus mu by E into like the sigma z plus sigma x. Meaning is again simple, there is a minus sign is there because of the contraction in other two direction, because if you pull in one direction always there is, you see the reduction of the dimension is there in other two directions. So that is what you see, the minus sign will always be introducing in those things, and if you are counting the epsilon z in the z direction when the load application is in the z direction, then epsilon z is nothing but equals to sigma z by E minus mu over E into sigma x plus sigma y. So you see here, if you are like going for a generalized part, then you will find that we can simply compute the these strain component in x, y and z correspondingly with the combination of sigma x, sigma y, sigma z in individual direction also. So in this following analysis, shear stresses were not considered. That is the key point here. Like till that only we found that sigma x, sigma y, sigma z, because you see these like the normal stress components are only acting, and due to that you see we have the deformation, and it can be computed with the using of the Poisson ratio and the direct stress component. So that part we discussed, but if the amazing thing is that still there is no shear component was there. So it can be shown that for an isotropic material, a shear stress will produce only its corresponding shear strain. Means you see there is no shear stress, the shear strain component will come in form of deformation until unless the shear stress is not there. And you see we cannot like influence the axial strain, and because of the axial strain even we cannot say that the shear strains are there, because you see the deviation in the angle is. Thus you see we just want to write the Hooke's law for individual shear strain and stress in the different manner. You see here, if the shear stress is there, the gamma xy, it will induce the shear strain in this particular like due to the tau xy shear stress we have gamma xy. So gamma xy is equals to tau xy divided by z. So now you see here, as far as the axial strains are concerned or the normal strains are concerned, the new modulus of property was there, that the Young's modulus of properties. But here you see, since we are talking about the shearing of plane, so due to the shear stress present, as we said that the shear strains are there, that means you see this Young's modulus of property is not at all valid, then we need to define the new modulus, that is the shear modulus of elasticity, and that is denoted by the z. So z is only valid whenever the shearing is there, and E is only valid whenever the axial stress and axial strains are there. So you see these two different properties of materials are there, and they are exhibiting the different value in terms of the types of load. If the tensile loading is there or the compressive loading is there, then E will come. If the shear loading is there, then the G will come. So if we are talking about the xy plane and the shear stress is there, this tau xy, so the shear strain will come gamma xy is equals to tau xy divided by z. Or we can say similarly in other two planes yz and zx, similarly the shear strains will come, and the shear strain in yz plane means if we have the y and z plane, then we can this gamma xy is nothing but equals to tau xy divided by z. Or we can say also if we are talking about the zx plane, then this gamma xz is nothing but equals to tau xz divided by z. But this relation within the shear strain and shear stress is only valid when there is a elastic limit is there. So you see here the all equations right from first three, this epsilon like x, epsilon y and epsilon z, or we can say this gamma xy, gamma yz and gamma zx, all 6 equations are known as the generalized Hooke's law and are like constitute the equations for the linear elastic isotropic material. That means you see here this is only valid when we are taking the material property within the elastic region of the isotropic material, then we can say that all 6 equations which we have shown here, 3 for the normal strain component, 3 for the shear strain component, are only valid. When these equations are used as written, the strain can be completely determined from the known values of the stresses always. Because you see like whenever the load application is there, the stresses are first forming, and because of the stress formation the strains are there, and if you want to maintain the equilibrium for that, always there is a counter evidences are there in form of the stresses only. So strains are always coming due to the stresses, and if you want to compute the strains, the stress the component of the stresses are always there in that. So the to engineers the plane stress situation is much of reference, because you see always we are keeping always we are talking about the plane like that, what xy plane is there, yz plane is there, zx plane is there. That means you see like the third axial stress or third axial strain is always going into the 0. So either sigma z or tau xz or tau yz means the normal stress component or the like this other shear stress component in other directions are always keeping 0. So we can say the above set of equations, whatever we have written in the previous 6 form, it can be again you see reduced to the new form, that because if we are keeping sigma z is 0, we are keeping tau xz is 0, we are keeping tau yz is 0. So the new form of these 6 equations are: first, the normal strain component in the x direction, epsilon x is nothing but equals to sigma x minus E, sigma x divided by E minus mu times of sigma y by E, because minus mu times of sigma z by E will gone. Similarly, you see for y direction, this epsilon y is nothing but equals to sigma y by E, this is the dominating parameter, minus mu times of sigma x by E, because minus mu times of sigma z by E will eliminated here because of the plane strain and plane stress. And third you see the epsilon z in the z direction, which will come due to the load application in the x direction. So you see here minus mu times of sigma x by E minus mu times of sigma y by E, or you can say minus mu times of sigma x plus sigma y by E. So you see it is the induction, or we can say the interaction effect of these two stress component x direction as well as the y direction. Or also we can say that you see the stress component in other direction, xy direction, it can be easily come that tau xy is nothing but equals to gamma xy by z. So you see these are the 3 equations, and if you see the inverse relations, it can be also well set up. It can be also determined with the following relations, that sigma x is nothing but equals to E over 1 minus mu square into epsilon x plus mu times of epsilon y. That means you see now we have the total, like if you know the deformation in x direction, if you know the deformation in y direction, you can set the relation with the using of Poisson ratio and Young's modulus of elasticity, and you can get the value of the stress in the axial direction. So if you want to compute the stress in x direction, we can easily compute with the using of E, Young's modulus of elasticity divided by 1 minus mu square Poisson ratio square into epsilon x plus mu times of epsilon y. So you see epsilon x and epsilon y can be measurable, put those value and get the value of sigma x. Similarly, you see you can also get the value of sigma y, which is again similarly you see computed E over 1 minus mu square epsilon y plus mu times of epsilon x, because you see here irrespective of sigma x and sigma y, what kind of load application is there which is more of dominant nature. So we can easily use these things, and you see as far as the shear stress is concerned, again it is pretty simple, simple to get those sigma xy, which is equals to modulus of elasticity z times this gamma xy. So you see these either irrespective of the straight relation, because now the these 6 relations can be merged into 4 relations of the generalized Hooke's law, as we can see here these 3 normal strain component and the shear strain component 1. So these 4 relations are only applicable whenever we are going for the plane stress and plane strain, or if we are talking about the inverse problem, but can easily compute sigma x, sigma y and this tau xy for our calculation part to observe the stress values if you know the strain values. So Hooke's law is probably the most well known, and widely used this constitutive equations, which one cannot say that all the engineering materials are linear isotropic ones, because you see this is the perfect limitation of the Hooke's law, is that we cannot say that actually these all whatever the material which are available in this universe, they can show the perfectly linearly. First, linear means the this stress is proportional to strain, and the elastic also within this elastic region they will show, and isotropic. So like we can say this is the perfect limitation for the Hooke's law, is that these equations are valid within this region only, and that is why you see it is not we can say the generally acceptable for all the materials which are applicable in this universe. Because now in the present times new materials are being developed, and every day you see these fibers, composite, polymers, all those materials are available, and they are exhibiting the unique feature there for a specific kind of application. So you see many useful material exhibit the nonlinear responses, because generally and that is why whatever the material which are or we can say whatever the responses are available in this universe, or we can say the realistic part which is very close to the nature, always non-linear. You can take any example and you will find that any process, any material, they are always you see exhibiting the non-linear responses. So that is what you see the first, when they are exhibiting the non-linear responses in between the stress and strain, we can say that you see this Hooke's law is not at all valid for those things. So again you see we have to be very careful that actually if they are showing the nonlinear relationship between the stress and strain, or if they are not showing any elastic region straight away, if some sort of plasticity is there in between that, then we can say that this Hooke's law is not at all valid. But the beauty of this Hooke's law is if it is if you are apply the load, and if it is within the linear elastic region, whatever the these relations which we have shown previously, all the 6 relations for all 3 dimensions, or 4 relations for 2 mutually perpendicular directions, they are absolutely valid, and it is pretty easy to calculate those required parameter for that. So now you see, as far as the plane stress is concerned, in many of the instances the stress situation is less complicated. For example, if we pull one long thin wire of a uniform section, means if you have a thin wire of a uniform section, and if you are pulling, then always we will find that actually it is more of the uniform nature, the load application is pretty uniform, and whatever the area reduction is there, this is also you see sort of symmetric. There is no stress concentration is there at the different points, kind of that. So we can say that actually we can simply find the small parallelepiped which is symmetrical like in the x direction, where the x is always you see towards that part, towards the main direction where the load application is there, and only we need x as well as the y direction for total description of the stress. So we do not have to go for the complicacy of those things. So generally you see whatever the material, like you see we have like the RCC rods are there for making the building. So always we found that actually they are having a good tensile loading is there. So means only to analyze that kind of thing, we know that what kind of loading can come on that way, axial loading is there, or you see whatever the compressive part is there, but it will come in the plane part only. So we do not have to go for the complicacy to analyze those kind of things. Only you see the small reasons and the simplicity of the stresses are well stabilized, and it is much of the information is already being described from those kind of things. So these plane stresses are always you see playing a key role for ease of analysis. Then you see, so if we want to take any xy plane, any of that, you see all 3 components or stresses can be easily described, as I told you in the previous slide, that sigma x, sigma y and tau xy easily can be described on the plane when you have a simple parallelepiped, and you see sigma x is there in the x direction, sigma y is there in the mutually perpendicular direction, and this tau xy is there in the this parallel surfaces are there for you see the clockwise direction or counterclockwise direction as far as the rotation is there. So we can easily show their nature of that, how they are what is the nature, tensile, compressive, clockwise, anti-clockwise as far as the shear is concerned, and also we can show that actually because of these things what will be the this combined effect is there on the this parallelepiped. So this combination of the stress components are always called the plane stress situation, that actually the 2 mutually perpendicular stresses xy, and you see the shearing is there on the top of surface. So that is what the plane stresses are well stabilized stress formation is there, and if we are going for the complicacy like in that stress, this tensile form of the stresses, always it gives you a complicacy, and like for calculating all those parameter and all the different kind of loadings are there, it will be very difficult for like analyze the things. So that's what you see, we always prefer to be analyzed based on the plane stress, as we discussed in this lecture, in this slide. So now you see a plane stress may be defined as the stress condition in which all components associated with the given direction, like you see the if you are saying that the z given directions are supposed to be 0, like you see if I am saying that the xy is there, so always sigma x, sigma y, tau xy will come, so other component, the z component will gone out, so sigma z, tau xz, tau yz will be gone out. Or if I am talking about the yz plane, then x component will gone, sigma x will gone out, or tau xz, tau yz will gone. Or if I am talking about the yz plane, then only the respective parameters will come, like sigma z, sigma y. If I am talking about zx, then sigma z and sigma x will be there, and tau zx will be the dominating parameters are there. Meaning is very simple. Whatever the plane which you are considering, the dominating parameter in terms of the normal stress and the shear stress will easily like located, and we can simply see the observation of that how they are like putting their effort, and how we can cumulatively, means what is the combined effect is there of those stress component. So now you see the last part of this our lecture is the plane strain, because as we know that the plane stress is playing a key role for the formation of the stresses in this, then what about the plane strain? So if we focus our attention of a body whose like the particles are all lying in the same plane, means there is no change in the plane, they are exactly well set up within the plane, and which deform only in the plane only, then you see we do not have to go for all the other parts of the deformation and complicatedly you see analysis those things. So this deform only in the one plane, this type of deformation is called the plane strain, and you see like this situation is very generalized situation. So if I am saying that actually if I am taking xy plane where the plane stresses are there in x and y, and sigma x and sigma y and tau x y are the dominating stresses are there in these things, the third stress component and the normal as well as the other two shear stress component, these are 0, then similarly you see the strain component are also like deriving from those kind of relations, and we can say that this epsilon z will be of also 0, because you see there is no this stress component is there, sigma z is 0, so obviously you see epsilon z will also be 0, and similarly you see the other two components of the shear strain, the tau zx and tau zy will be also 0, because you see in the plane stress also we compute that the tau zx and tau yz will be 0. So gamma xz and gamma this zy this will be 0, because you see we are not considering any kind of deformation in the z direction irrespective whether it is a normal or the shear strain is. So we can say the non-zero terms are only 4 terms, only 3 terms if we are taking the this xy plane. One is the epsilon x and epsilon y, these are the two normal strain component, and third one is the gamma xy, which is you see this shear strain component. So if strain components epsilon x, epsilon y and gamma xy are always they are presenting and the angle theta is specified, then it is pretty simple, you see like it will give you all the kind of required information which you want to analyze, you see for a plane strain. If you want to cut the like the inclined plane, and if you want to measure that what will be the strain component as their epsilon theta and this gamma theta, then you can easily get with the using of these 3 components, epsilon x, epsilon y and gamma xy. So we can say that actually these components are well enough, like it will give the whole information about any kind of body. So that's what you see, you don't have to go for all like the 6 parameters within this generalized Hooke's law, only these 3 parameters are well enough to like give all kind of information with respect to some other axis can be easily find it out. So this is you see the plane strain. So the plane stress and plane strain, so that's why you see generally if we go further our analysis is mainly based on the plane stress and plane strain. That's why you see we discussed thoroughly here that why plane stress and plane strains are necessary and good enough to analyze any kind of structure in which these 3 types of loadings are there, two mutually perpendicular like the normal loading and the shear loading is there. So you see in this lecture we discussed about that, like the if we have the different variety of the material, then how we can express the stress strain curve, the idealized stress strain curve for like exhibiting the elastic as well as the plastic region. Like, and if we have, you see, like if you are talking about only the elastic region, then there are two important properties which we discussed, that isotropic property, that you see all the material property, which if the material is showing all its property equal in all directions, then it is the isotropic property. And if you see material is showing at every point the equal property, not in all directions, then it is homogeneous. So these two properties are very, very important. And if you are saying that if you have a material which is linear following the elastic and isotropic material, then there are 6 like equations, 3 for the the normal stress component and normal strain component, and 3 for shear stress and shear strain component, and for which you see we defined the Young's modulus of elasticity for the linear like this normal strain component linearly, and if the shear modulus of elasticity for the linearly shear properties, for you see where the shear stress and shear strains are there, and we set up the relations. And then in the last part we discussed about that if we have like the plane stress and plane strain, then we don't have to like consider the third direction, we can simply put the 0 like instead of going the complication of the analysis. So you see sigma y or sigma z, sigma x and sigma y is well enough in the normal stress condition, and if you want to go for the shear stress, then tau yes, the tau xy is well enough for the required calculation. So you see this part which we discuss in this lecture, and in the next lecture you see we are going to discuss that actually how you see like we can put, if you see we have like go beyond the elastic limit. That means you see if we have a general, let us say the tensile bar is there, and if you are pulling that part, then how the material, if we are just talking about a general mild steel material, which I told you that it is a general elastic and plastic material, and if you are applying the tensile loading, then how it will exhibit not only the elastic region which we have discussed right now for Hooke's law, if you go beyond those things, then what are the different stress components are there, like you see the yield stress, ultimate tensile strength, because the tensile loading is there. And then you see if you are going up to the fracture, then what will happen, what kind of specific shapes are there at the time of rupture or fracture, if you are taking about if you are talking about the mild steel. And if it is a different material altogether, like you see if you have a material of the perfectly like elastic but plasticity is there, then you see what kind of the shape is there. So this kind of you see like the relation which we want to set up. And not only these homogeneous and this isentropic properties are well enough, we also like need to define that actually what will be the strain hardening is there, if you want to compute straightway from the graph itself, that what will be the like the this rigidity or the hardness or any other like the property of the material, then how we can get, and what are the impacts of these properties on the behavior of the stress and strain, or the behavior of the material to get the responses in between the stress and strain, we can easily set up. So you see this kind of relations which we are going to discuss about like the stress strain for the different material in the next lecture. Thank you.